Yes. First of all, I would like to thank the organizer for giving me this opportunity to speak about our recent work. And I'm very sorry that I couldn't be there, the venue, because I had some meeting that I cannot escape. So I am speaking from Zoom. Okay, I'm talking about assessing transfer entropy from biochemical data. This is a joint work with Takuya Imaizumi and Nobuhisa Umeki and Ryo Yoshizawa and Tomoyuki Obuchi and Yashisako. Okay, this is the purpose of today's talk. Okay. Recent advancement of measurement techniques makes it possible to collect many data like never before. This raises expectations for the data-driven approach, particularly in research on complex systems where finding first principles is difficult. However, extracting useful information from data is generally challenging. Today, I talk about our recent attempt to read information flow from biochemical experimental data, okay? So this is outline of my talk. Let me see, pointer. Right, okay. Oh, sorry. Next, I will introduce a background of my talk and introduce a target system. And the sub part is the main part. I introduce the transfer entropy. What is the definition of the transfer entropy? And presents the developed method to assess the transfer entropy from the data. And we applied our method to some real biochemical data and conclude with summary. Okay, the background. The background of this talk is systems biology. The goal of the system biology is to understand biological organisms as systems. So the slogan is that not in reductionism, but in holism. And much effort has been made in the last two decades. The bioinformatics and data analysis and mathematical modeling of biochemical reactions by ODE, PDE, and SDE, etc. And there are many graphical expressions of reaction cascades and chains are discovered. So this figure shows the concept of the system biology. So we want to understand biological organism from genome to life, okay? But this is very challenging problem, so it takes a long time. So we here focus around here, right? The sub-goal. So sub-goal of this talk is signal pathways in ERBB-RAS-MAPK system. This is an intracellular signal transduction system, okay? This controls cell fate, division, and differentiation, apoptosis, etc. And if some disorder occurs, this is the cancer and genetic disease. And for this system, multi-species simultaneous measurement is possible by fluorescent labeling. So here, so this is a schematic picture of this system. So we give some stimulus around here, and then some chemical reactions occurs at the cell membrane. So this is the proteins, GLB protein, and this react with Sheck proteins, and these reactions constitute a cascade, right? And this causes a reaction with the RAF, and finally it propagates to the cell nucleus. And By using fluorescent labeling, we can observe or measure the activities of the two, for example, in this case, two proteins, graph and shape, like this. Okay, we can get this kind of time series. Okay, what I want to know is that there should be some information exchange between the two time series. So what we want to do is to quantify the how much information and when the such information are transferred between the two. Okay, this is the goal of our research. And for this system, what have been done and what have to do. And what have been found is that, as I showed, relevant proteins were found. And also, the pathways of their reactions were also found. Okay, so next step, we should do the following. So assessment of the amount and the timing of information propagation over the pathways. Okay, this is because biomolecular species are just a media for the transmitting information. Okay, and what actually controls cell fate is information. So we want to know the information flow from the data. For this purpose, we focused on the transfer entropy. This is because this is a universal measure of information flow between two time series proposed by Schreiber 2000. This is defined by this formula, okay, based on the joint distribution between the two time series. So implications, okay. Transfer entropy is defined by the difference between the two conditional entropies. First term is that the HYT bar HT minus 1Q. This represents the remaining uncertainty of Y at time T given its past Q state. Okay. And this one, the other one is that this represents remaining uncertainty of Y at time T given the past P states of X on top of the past Q states of Y. Okay. So the transfer entropy, this is defined by the difference between the two, represents the amount of improvement of the predictability about YT by knowing the past P states of X on top of the past Q states of Y. Okay. And this is a universal measure based on Shannon entropy. And unlike the mutual information is defined by this formula, the transfer entropy is asymmetric between the X and Y. So this is suitable for characterizing information flow from X to Y. Okay. But there are two difficulties in assessing the transfer entropy. Actually, transfer entropy, not only transfer entropy, but generally entropies are functional of high dimensional distribution. For example, this is a conditional entropy. It is defined this formula, right? So the first, it is difficult to characterize or estimate high dimensional distribution Q from data. Yes. Is generally difficult. Okay, this is very high dimensional distribution. This is a distribution of the time series. So characterizing or estimating this distribution is generally difficult. And even if the distribution is given, carrying out high dimensional integrals, right, is computationally difficult. Okay, so for these reasons, most existing studies have been limited to the analysis in small and or stationary systems. For example, this one. Actually, existing studies are classified mostly in the two categories, model-based and data-driven one. The model-based one is further classified into two categories: understanding of the implications of transfer entropy or its criticism. For example, Schreiber, Barnett, and Smirnov, etc., etc. And the other one is assessment for the theoretical models. Okay, the setting some small theoretical model and evaluate transfer entropy. On the other hand, data-driven approach. There are a lot of data-driven approach, economics and nervous systems, gene regulatory networks, and also the climate studies, as before, paleoclimate. But most of the data-driven approach is under the stationary assumption. But our target is like that: non-stationary and non-linear and high dimensional. But on the other hand, we can get order 100 samples, okay, for this system. Okay, so we tried various methods to evaluate transfer entropy, this type of data, and finally reach this conclusion. Almost unique practical choice is modeling by Gaussian distribution. Why? Because for the Gaussian distribution, exceptionally, we can get the entropies by analytical method. Okay, this is the general formula of the condition of this the entropy, but for the Gaussian distribution, this can be expressed by the conditional variance. And for the conditional, in general, conditional variance is difficult to estimate from data in general. But in the case of the Gaussian distribution, we can employ the sure complement formula. So evaluate this from the full covariance matrices. So if we can estimate the covariance, full covariance matrix from data, we can assess the transfer entropy by this formula. Okay, so this is fine. But there are still two remaining issues. The first is the sample size enough to accurately estimate the covariance matrix. Actually, it is related to the experimental limitations. Up to a few years ago, only the 10 samples were available. But recently, we developed some method which can collect about 300 samples. So maybe this is okay. The first issue may be okay. But we have the other issues, the check of statistical significance. This is because biological data normally includes the large statistical fluctuations. So the statistical fluctuation is not negligible. So we have to evaluate how significantly we can accept the result, right? So we have to check the statistical significance for the obtained result. But for this purpose, we need some sampling distribution, okay? But unfortunately, the transfer entropy is some complicated function of the data. So it is very hard to obtain the sampling distribution analytically. So what we the strategy what we took was a numerical check by bootstrap method. So this form. The bootstrap method is proposed by Efron in 1981. And this follows the plug-in principle. So the construct a sampling distribution handling the estimated distribution as if it were the true one. Okay. So in our cases, the relevant parameter is a covariance matrix that characterizes the Gaussian distribution. And of course, it is impossible to have the true covariance matrix from data. So we handle the estimated covariance matrix as if it were the true one. And based on this one, this covariance matrix, we evaluate the confidence interval by this procedures. Okay? Handle the estimated covariance matrix as a true parameter. Then evaluate the empirical distribution of transfer entropy by repeating the following steps many times, B times, right? Generate a sample from the estimated Gaussian distribution and evaluate the transfer entropy from the sample. So like this, we sample from the estimated distribution B times, and for each we evaluate transfer entropy, right? Then we can construct a histogram, and from this histogram we evaluate the confidence interval, right? And also, in the similar by the similar strategy, we can evaluate the statistical significance by constructing a null hypothesis. Okay. So construct a sampling distribution, designing a null hypothesis from the estimated distribution. Okay, what is the null hypothesis in this case? Is that the X and Y are statistically independent. This is the null hypothesis. Okay. In terms of the covariance matrix, this is represented by setting the covariance components, cross covariance components between X and Y to 0, right? So we handle this covariance matrix as if they are true one, and do the same procedure as before. So evaluate the empirical distribution of transfer entropy by repeating these steps B times. Okay. Then we can construct histogram of the transfer entropy and evaluate the chance level. Okay. Okay, but it is a kind of heuristic, so we have to check this method whether this method work or not work. So we tested the proposed method by application to a very simple solvable model. Okay, so the very simplified model of reaction chains characterized by these equations, right? At t equals 0, we provide some pulse signal, pulse stimulus for this component. This component corresponds to the X, this observed one. And the stimulus propagates to the right direction. And for the D step, after the D step, we observe Y. Okay, and the dynamics of this component is described by this one. Okay, at time t equals 0, a stimulus is given at the U1, and the stimulus is propagated to the right direction, like this one. And for each time, we observe the U1 and the UD. These two components correspond to the X and Y. So we evaluate how the transfer entropy from X to Y and y or the y to x are observed. So, and actually this process is a special case of state space model. In general, it is defined by this stochastic difference equations, right? Unfortunately, for this process, we can evaluate analytically the equal time covariance and different time covariance by this recursive formula. Okay, so given that these system parameters ft and ut and the covariance noises, even if the dynamics is time varying, we can evaluate the full covariance matrix. And based on this, we can evaluate transfer entropy from x to y and y to x as a function of time t. And we show some results for simple cases for d equal 4, right? So we provided pulse stimulus at time equal t for u1, and it propagates to u4. We always, anytime we observe x and y. Okay. These four panels represent the transfer entropy as depending on the time lags of x, lag time of x and lag time of y, right? Okay. So P is a lag of x and Q is a lag of y. Okay. Then we can see the following two characteristic features. The first is that actually for all panels, there are a little dependence on y's lag Q. Okay, we drawed 3 curves here, but they almost overlap, so we cannot distinguish the 3. Okay, this is the first characteristic feature. And second is that peak value. We can see there are peak of transfer entropy at time equals 3, t equals 3. But the peak value at time equals t equals 3 suddenly jumps up when x lag p reaches d equal 1, d minus 1 equals 3. Okay. So we can get this kind of the transfer entropy from x and y, x to y. And actually in the reverse direction, y to x, transfer entropy of y to x equal always 0. This is theoretically guaranteed. Okay, so understanding these two features, we take into account the two key properties. Actually, for this particular case, there are two key properties. First is that self-memory decays very fast because the damping factor is 0.5. So by one time step, the value of each component becomes half. So, so self-memory decays very fast. And since this is an influence from the left component, okay, the influence from the left component reaches without decay because the prefactor of this one is the 1, so no decays, right? So decay fast for the self-memory and efficient transmission from the left neighbors. These two are very key points to understand the behavior of the transfer entropy in this case. Okay, first, y little depends on y's lag Q. Okay, this is because okay, this is direction is the represent time step, this direction represents the components, the position of the components. Okay. You can see that y little depends on its past states. Okay, only influenced by the left neighbors. So transfer entropy from x to y little depends on its own log q, right? So there are 3 logs here, but all of the curves are almost all overlap. And y low peaks at t equals 3 for p equals 1 or 2. You can see this is t equals 3 cases. We evaluate transfer here. Okay, actually, for the log 1 or 2, these two the values correlated with the t equals 3 of y of t equals 3. So it has some finite value here. But this value is a bit smaller by the self-decay. So the peak value is small, right? On the other hand, if the time lag of the x is larger than the 2 or 3 equal 4, the strong amplitude here and here. So there are some strong correlation between the two, right? So we can get large peaks here, and after the peak, suddenly the rapidly decays. This is because this activation decays first, right? The consideration. So these imply that transfer entropy somewhat quantifies the causal relation from x to y with a high time resolution. Transfer entropy x to y is maximized when the actual cause that activates yt is included in the past p states of x. So monitoring transfer entropy offers information about the causal relation. And actually, transfer entropy is practically equivalent to a Granger causality when x and y obey autoregressive models. Okay. On the other hand, the finite transfer entropy does not necessarily mean interventional causal relation. So even if x does not actually act on y, finite transfer entropy can come out when they are statistically correlated. So this is a limitation with passive data-driven approach. For proving the interventional causation, active data acquisition, such as the lesion experiment, is necessary. However, transfer entropy is still useful to quantify information flow, particularly when the statistical physical pathways are known in advance, such as in the current intracellular signal transduction systems. Okay, but what we want to do is that to check whether such transfer entropy can be assessed from data. Okay, so far we evaluated the transfer entropy from the model, but what we want to actually do is to check whether the transfer entropy can be assessed from data. So we experimentally examined how accurately the theoretically computed transfer entropies are inferred from 200 pairs of sample time series of x and y. For this purpose, we carried out the bootstrap resampling 1,000 times for evaluating the 99% confidence interval and the 1% chance level threshold. So this is the result. Actually, there are 4 items for each panel. Green represents the theory, the true value, and blue represents the inferred value from the 200 samples. Light blue represent a 99% confidence interval, and red represent 1% chance level. Actually, the theory and inferred value almost overlap. It's very hard to distinguish the two. So, at least for this simple systems, it is very promising to evaluate the transfer entropy from data of several hundred samples, right? And but one caution is that inferred values positively biased, particularly for small transfer entropy values. This is because transfer entropy is by nature non-negative quantity. So even if theoretically it is zero, we can always get positive values from data. So it is necessary to take into account some biases when judge the confidence of the evaluated value. So we took some heuristic strategies that judge the statistical significance only when the lower bound of the 99% confidence interval is larger than the 1% chance level. But conclusion is that the comparison between the theory and the experiment indicates that a reasonable estimation of transfer entropy is possible from a few hundred samples of the two-time series. So it applied the proposed method to real data. Okay, in this case, we measured the two times series, source protein and rough protein. This is because that it is first reason is that these two proteins are intensively studied, and actually for this system, a wild type case, wild type source, there is some feedback loop here, right? And if the source is a mutant, okay, it is known that there is related to the Noonan syndrome, some genetic disease. So Noonan syndrome is like that. So symptom of Noonan syndrome is that morphogenetic abnormalities and mental retardations. You can see that here, this is a typical case. The bone of the two, these two bones placed in the asymmetric positions. This is a typical symptoms. And it is a rather common genetic disease, and 1 in 1,000 in Western countries. Actually, this is 10 times of the Japanese cases. In Japan, 1 is 10,000. And it is known that 60% is related to the mutation in the RAS-MAPK system, and 13% is related to the mutation of source protein. Right. Okay, but in molecular level, not still fully understand the mechanism. So we want to get some information from the data analysis, right? So this is a raw data, measured data. Okay, this is the wild source case, and this is a mutant source case. Okay. And these activities are the difference of fluorescence intensity from that before stimulus. Okay, so peaks, we can find the peaks source 5 to 6 after the 5 to 6 minutes after stimulus, and for last 8 to 9 minutes. So 3 minutes difference. But you can see that between the two, we can find a little difference between the wild type and the mutant cases in these single species profiles, right? So we analyze them by the conventional correlation analysis. This is the wild type source case. This is the mutant source case. Okay, but between the two also we can find little difference between the wild type case and the mutant source case again. So we applied our method for evaluating the transfer entropy. Okay, this is for the wild type case. This is the left panels represent the source to RAF, right panels represent the RAF to source. Okay, these red arrows represent 1% significant transfer entropy. Okay, and you can see that source to RAF is left panels. We find large peaks after the 1 to 2 minutes after stimulus. And you can find also the some peaks for RAF to source after 3 to 4 minutes, right? This probably means that there is feedback. This is consistent with the biological knowledge. And also observed even after several 10 minutes here, right? Here. So what happens for the mutant source case? Actually, we can find large peaks for source to RAF. It is larger than the wild type case, okay? But we cannot find any the significant peaks for RAF to source. So this probably represents means lack of feedback loop. Okay. So transfer entropy distinguished the wild type and mutant source cases. In contrast, low signals and conventional correlation analysis, we cannot find a significant difference between the two cases. And our method is user-friendly, performed by only estimated covariance matrix, low computational cost, and no need for modeling the process. Okay. Actually, we model, but it is model the system, but it is in the distribution level. So we consider that this may be promising as a practical tool for cause finding of genetic disorder. So summary. Okay, let us wrap up my talk. We developed a method for inferring transfer entropy from multiple samples of non-stationary time series. Based on the Gaussian approximation and bootstrap method. And method validation by a solvable model suggested that the method offers reasonable estimates from a few hundred data samples. And the application to real data managed to detect difference between the wild type and mutant systems that were related to genetic disease. And it was difficult by conventional methods. Okay, although we limited our target to biochemical signals, the developed method is potentially applicable to data analysis of wider domains. If the data is stationary, any time series. Non-stationary case, a system where the order 100 samples are available. Probably the simulation data and the transportation system and etc. And future research direction is analysis of other data and reduction of necessary sample size and beyond the Gaussian approximation. Okay, maybe we stop here. So thank you for your listening. This is a reference of this talk.
Thank you, Yoshiyuki, for the talk. Are there any questions? So I will kick off with a couple of questions. So the first one is about, so you said this is quite a general method, but you've used it for a single data, single problem. Have you tried beyond the single problem?
Okay, we are trying, actually we are trying, but what we need is multiple data set, okay? Multiple pairs of the time series. Actually, the targets that we can get multiple time series are a bit limited. Okay, biochemical reactions, okay. Okay, but other cases, non-stationary cases, it is a bit difficult to find such systems. Probably the stationary cases, maybe we can apply this method. For example, the nervous systems or the other, for example, maybe the climate system also okay, if we can regard the system is stationary. Okay, but okay, for the similar problem that we showed here is a bit difficult to find. So we are now looking for such targets.
Yeah. Okay. I have another question, which is how can you actually validate your results, because you don't have the ground truth, right? You can check it on synthetic data, but then for the real data, how can you actually validate that what the results that you obtain are correct?
In our case, we can do experiments. For example, by doing knockout experiment, we can validate. So we are now collaborating with experimentalists. So this is one kind of one of the future research. But in this case, we can do that. Okay, lesion experiment, the knockout experiment.
Thank you, Jürgen. You have I don't know.
Yeah, very interesting talk. I have a question: which kind of nonlinearities with model systems could you handle with this approach? Have you checked this a bit?
Yes, maybe we should do that, but we didn't do that yet. But for example, this kind of chemical reaction case, we have some model. Okay, so probably first we should do is that first we generate some data from the nonlinear stochastic equations and evaluate by our method, and also from probably by describing the process by the Fokker-Prompt equations, we can get some distribution, right? Then we may be able to evaluate it from semi-analytical way and compare our data-driven analysis and some semi-analytical method, the result, like that.
Thank you.
Any other questions? Yes, please.
Yeah, thank you for the nice talk. Because biological data are not necessarily Gaussian, I wonder what the best way to evaluate how good the Gaussian approximation was. And suppose you see a deviation from Gaussian, but the deviation is not too large. Is there a way to correct your results to take into account that deviation?
Okay, thank you. Actually, the first thing is, this is the first approximation, okay? Actually, data is not fully Gaussian. We noticed that. Okay, this is one. This is the time series. Actually, this, I'm sure that this is rough and source, and this is source single. Okay, we can find that this is somewhat unimodal, right? But it has some non-trivial shape. So this indicates the true distribution is not Gaussian. Okay, so what we are planning is that evaluates the distribution as a mixture of Gaussian. Maybe this is doable. And the mixture version is yes, actually powerful. The method, and maybe we can approach to the real distribution.
I see. Mixture means a superposition of two.
Of Gaussian, yes,
Gaussian-
superposition Gaussian. Yes.
I see. I see. Thank you very much.
Just a comment, mixture of Gaussians will be difficult to integrate in order to calculate the transfer entropy.
Yes, yes, but still, yes, incorporating some the MCMC method, still I think doable.
Okay. Good. Any other question? Okay, so let's thank the speaker again.
Thank you for your listening. Thank you.